Hi everyone and welcome to today's video on measures of centre and spread. Wow, does that sound exciting? Well, actually it is, and it's going to scaffold the rest of the learning for all of the probability videos I'm about to do. Now we're following the Cambridge Essentials textbook series here in Australia, which I think is applicable to the rest of the world. Now if you think about spread as in cheese spread or Vegemite or Marmite, can't stand the stuff, yes? Well actually, coconut please, yeah, coconut. It's not that type of spread, it's about how spread out the data is. But by the end of this video, as I say here, we're going to be looking at the expected value, what it means, variance and standard deviation. Now we've been doing a lot of mean, median, mode and range all the way from about year 7. And all that was trying to do was find you how spread out the data was and how close to a particular center point it was, or where the center of that data was. The median, if you remember, was really, really good if we had an outlier. The mean was really, really good if the data was sort of relatively packed together. Now we're not going to deal with range and we're not going to deal with medians. We're just going to look at expected values. And you're going to say expected values. I'm going to say yes, because that's what we call it in methods or in A-level or whatever else. So you're going to say, well, what is this expected value? Well, that's what the video is about. Chill. Here, too long, don't read. That's what the TLDR means. And those are all of the formulas we're going to look at in this particular section of the video. What is important is please, please, please understand what it is you're finding, because it's going to be used over and over again. All of these formulas for at least the next probably about 12 videos, are all going to be used in different forms. So take a screen grab, put it in your summary book, and PDF notes will be actually coming out, and I'll put them in the link below when they're ready. They'll also be on my website, which is also in the link below. But I suppose we should say, what does expected value mean? What does expected value mean? Well, when I toss a coin, and look at that finger, fabulous. When I toss a coin, if I was to do it, say 10 times, would I expect the probability of heads and tails to both come out 0.5? If you're really, really lucky, it will, and then you can give up the experiment and go, thanks very much. But the chances are it won't. 10 isn't really enough. What about 100? Well, actually, if you did 100, the chances are you'd probably get closer to 0.5, but maybe even then, not 0.5. What about 1,000 throws? Well, who's got the time to do 1,000 throws? But what you'll tend to find is the more throws I do, and I work out my probabilities, the more that this graph will get closer and closer to a particular value. In the United Kingdom, I used to do one where we dropped thumbtacks or drawing pins. And we used to get kids to draw graphs. And what we did was for every 10 throws, they reworked out the probabilities cumulatively. And so for the first 10 throws, they might have had a probability up here of it landing point up, for example. And then the next 10 throws, it might have been down here, and then here, and here, and here, and here, and here, and here, and here. And what we found was that the graph, the more throws we did, tended to wobble, getting closer and closer to this expected value. Yeah, so in this situation, I think it was about 0.73 was the expected value of landing point up. But it's this wobbling effect that says, you know, it was going to get closer and closer to being more likely point up. How do we do this in methods or A-level or the subject you're dealing with expectation in? Well, we use a formula. And the first thing we notice here is that we have this Greek symbol called mu. Now, I did not go moo, because cows go moo. Not interested in that. It's mu. It has a very definite pronunciation. Now, mu also stands for the same thing as E of x. So, because maths is trying to trick you, mu, expected value, or mean all means the same thing. And how do we find this? Well, we use this rather funky thing here. Now, first things first, and I know why my computer will not put the x underneath the e. I need to find a better equation editor. But what that means is sum. And if you've used Excel, you'll notice that there's the little sum button up there that'll add all those numbers together. And that's what sum means. It says sum for values of x times p of x. And you're going to say, what's this x times p of x, isn't it? Well, did you watch my previous video on discrete random variables? Well, if you did, then you'll know what this table here means. So if I was to define x as the number of white balls taken out of a bag there, and I'm taking 3 balls out, then the values that it could take is I could either have no white balls, 1 white ball, 2 white balls, or 3 white balls out of those 3 taken out. And below are the probabilities of getting each of those various outcomes. I'm going to rub this out to make it a bit clearer for myself in a moment. But what this formula here says is effectively do this times this, this times this, this times this, and this times this, and then add them all together. Easy, huh? Well, I think so. So we're now going to say then that mu, which equals e of x, is equal to 0 times 0.064 plus 1 times 0.288 plus 2 times 0.432 plus 3 times 0.216. Now, I don't need a calculator to help me with that one, and I certainly don't need a calculator to help me with that one, but I certainly do need a calculator to help me with this one. So, if I now fire up my trusty calculator and do 2 times 0.432, oh dear, 2 times 0.432, I'm going to get 864, 0.864, and if I do 3 times 0.216, I know you can't see my calculator screen, but don't worry about it, 0.648, which means when I add all those together, what do I get? I get 0.288 plus 0.864 plus 0.648 gives me a grand total of 1.8. What does that mean? Well, that means my expected number of white balls being taken out of a bag, if I'm taking 3 out at a time, is 1.8. Now, that doesn't make a huge amount of sense because I can't have 1.8 balls. But expected values can take decimal points, and so we don't really worry about it. So can I use the same idea to help me find this expected value of 3x plus 1? Now, first things first, what does that even mean? Good question, new video. That's like an hour in itself. But what we can do, and I've obscured it here, is use this formula here. And what it says, if I want to find the expectation, in fact, of anything, and I'll just put a comma, I'm going to sum for all values of x of that something times the probability of getting it. So in this situation, if I'm trying to find the expectation of 3x plus 1, I'm going to sum 2x, 3x plus 1 times p of x. Now you're going to say, what's this 3x plus 1? Well, again, we have a table. And it just so happens that 3x plus 1 means take the original x values, which were 0, 1, 2, and 3, multiply them by 3, and add 1, and then effectively repeat the process. So I've already set up my table. I'm going to multiply 0 by 3 and then add 1, which gives me 1. 1 times 3 is 4, that's 7, and that's 10. So now I'm not going to use this values anymore, not interested in that, because I want to find out my expectation of 3x plus 1. How do I do that? Well, exactly the same as I did. The expectation of 3x plus 1 is equal to the sum to x of 3x plus 1 times the p of x, which equals, right, so 1 times 0.064 plus, I'm going to write it long down way just so I don't run out of space, 4 times 0.288, 7 times 0.432, and 10 times 0.216. Let's load up my trusty calculator. What do we end up with? Oh, grasshopper, 0.064. We don't need to multiply that by 1 because I can do that in my head. Plus 4 times 0.288 plus 7 times 0.432 plus 10 times 0.216. Gives me the grand total of 6.4. So that's equal to 6.4. Now, it doesn't actually matter what I end up doing in terms of the expectation, just so long as I take my table here, create a new row, multiply x by whatever's in there, and then recalculate it. I love expectation, but the good news is, ladies and gentlemen, there is a shortcut. And you're going to say, really? And I'm going to say, yes, because what we now know, or what theory suggests, and actually having to prove this is a bit beyond this video, and in fact, probably the course, is if I want to find the expectation of something x plus something, I can actually do a times the e of x plus that something. So actually, if I've already worked out the expectation of x, I can just multiply by whatever that value is, and then add whatever that value is. Now, we knew previously that e of x was equal to 1.8. Do you remember? So that would suggest that the e of 3x plus 1 is 3 times the e of x plus 1. 3 times 1.8 plus 1. And then firing up my trusty calculator, I get 3 times 1.8 plus 1 gives me 6.4 result. So knowing these shortcuts is actually really, really helpful as well, particularly later on when we work out things like variance. And that is a perfect segue into variance. Yes, ladies and gentlemen, here is our variance. Now, variance is really, really interesting because what it is a way of working out the average distance the data is away from my mean point. Now, you're going to turn around and say, well, what does that mean? Right. I'm going to draw a graph, but I'm going to draw it horizontally because hopefully this will sort of make sense. Imagine I have data items here, 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 and here. And I work out my average value. Now, hopefully what you'll realize is that that average value will end up being a dotted line somewhere through the middle of that. Yes? Now, generally speaking, we would draw curves that go up. I'm just going to draw a straight line for reference. So if I was going to look at the distance here, and there, and there, and there, and there, and there, and there, away from the lines, then I would be looking at the average distance. But as it stands at this moment in time, all of these differences are positive, and all of these differences are negative. And if I add them together, guess what you're going to end up? You're actually going to end up with a value of 0. Now, why do you think you end up with a value of 0? Well, simply because that's the whole point of the average value. So I need to find a way of actually fudging my data, if you like, to try and get all of these negative values to be positive, because that's what's throwing things. That's what's evening this stuff out. And it just so happens that what we can do to the data is actually square it. So if I take each of my data items here and square them, then I actually turn all of these values below the line into distances above the line. Okay, it's going to be twice as big, or it's going to square the value away from it. But the point of it is, I'm then going to get an average value of the distance away. And that's what variance is. It's just a measure of the distances squared, or the square distances away. Now, that doesn't actually make a huge amount of sense, which is later on why we come back to standard deviation. But let's not rush things. Now, to find the variance of the data, we can actually use all sorts of information to, or there's actually two formulas we can use. Now, the first one is this one here. And I have to admit to you, ladies and gentlemen, I really don't like that. It's very rare in mathematics that we would use that formula. But just to explain it, just in case it ever came up in an exam, we would find the I can't draw the sum today. I don't know why. We would draw the sum of x minus mu squared times p of x. If you remember, that and this mean exactly the same thing. And you're going to say, well, how do I find that? Well, if I wanted to on this table, I'd add another column. And I'd have to find, I'd add another row, and I'd have to find my mu value first. How would I find my mu value? Well, mu is equal to expectation of x, which means I would do this times this times this times this and that, blah, 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 and add them together. Now, rubbing this out so it doesn't look too complicated in a moment. Then I would take that away from x, then I would square it, and then I would multiply. Now, I don't know about you, but that seems like a lot of work. And the good news is there's actually another formula, which says that to find the variance of the data, I can do the e of x squared minus the e of x all squared. Now, the good thing is, ladies and gentlemen, they are not the same, all right? So e of x squared and e of x all squared is not the same. So now I need to do two sets of calculations for this one. Firstly, we need to work out what the e of x is. Now we know how to do that. That's 0 times 0.08 plus 1 times 0.18 plus 2 times 0.4 plus 3 times 0.34. Firing up my trusty CAS will give me, we don't need to worry about that one, so 0.18 plus 0.8, I can do that one in my head, plus 3 times 0.34. 34 down, gives me a value of 2. So in that situation, my e of x is equal to 2. How do I find my e of x squared? Well, going back to that theory we did a moment ago, remember, whatever's inside here tells you add another row onto that table, square all the values, and multiply those. So just to highlight again, that's the sum of all x of x squared times p of x. So I'm going to do 0, 1, I'm going to write that as 4, and that one is 9. So, doing the same style of calculation, moving it up a bit, because I'm sure my head's going to do that, we get, once again, 0.00 times 0.08, 1 times 0.18, This time is 4 times 0.4 and 9 times 0.34. Putting those together on my trusty CAS gives me... let's clear my data. Let's clear all that so that we can got some space on the screen. Yes, please. I've just said clear. Why would you disagree? So we get 0.18 plus 4 times 0.4, which to be fair I could have done in my head, plus 9 times 0.34 gives me a grand total of 4.84. Have I finished the calculation? No, because I now need to go back to here and say, right, so that means the e of x squared, which is 4.84, minus e of x all squared, which is 2 squared, which gives me, so I'm going to take away from that 4, I don't know why I fired up my calculator to do that, but anyway, gives me a variance of 0.84. A lot of hard work, you think, but actually there are expectations that you're able to do this, particularly for SACs and exams and what have you. So that's how to find the variance. Always use this formula here. It's so much nicer. Now, standard deviation. What is standard deviation? Well, effectively, do you remember the variance we just talked about? Basically squared all of those distances above the line to allow it to all have some sort of average value. The problem is, when I squared all of those distances, it actually made a nonsensical unit. It didn't actually help us in any way. So guess what we do to turn it back into the units that we want? Well, we square them all to make them positive, and then funny enough, we square root the variance to turn it back into our original units. Right? So if, for example, we were doing heights in meters, then we would have squared it to get meters squared, which makes no sense because you can't measure heights in areas, random. And so we square root the variance, which gives us this thing called the standard deviation. And actually the great thing is the standard deviation is nothing more than a measure of spread. How spread out the data is. It's a numerical value that says whether the data is wider or shorter than something it's compared to. Now, standard deviations. We can draw a beautiful curve here. For lots and lots of data, we can actually fit it into what's called a bell curve. And this thing here is called the bell curve. And when we do it, then we notice that here is what we call my average value. We actually center this data around a value of mu. And then each of these values here stand for one standard deviation. So this is standard deviation, this is 2 standard deviations, and this is 3 standard deviations away from my mean. Everything is referenced to that middle value. Here is minus 1 standard deviation, minus 2 standard deviations, and minus 3 standard deviations. Being able to work out those standard deviations and consequently to know what area of the graph lies within that. So for example, for a standard, what we call normal distribution, 68% of our population falls between minus 1 standard deviation and 1 standard deviation of the mean. 95% of our data falls between 2 standard deviations of the mean. That's minus 2 to plus 2. And 99.7% of our data falls between minus 3 and 3. So this little section here, sorry, that's not that one there. This little section at the end, which says 0.15, is effectively a 99.95 ATARs if you're over here in Australia, or the people in the UK or America who are seriously bright. So we can use that information and certain notation to help us find values of probabilities. And again, we're rushing ahead in a little bit, but notation-wise, we're not going to get too excited about this for the moment, is this. This notation here says mu minus 2 sigma is less than 2 equal to x, mu plus 2 sigma. Now what that's saying is, find the probability, and I'll come back to that in a moment, that my data, my random variable, and what are we looking at this random variable? These are the values here of my random variable, 60, 90, 120, 150. This could, for example, be the number of minutes it takes me to complete my homework, or a group of people to complete the homework. This here, mu minus 2 sigma. What's this sigma business? Not heard that before. Well, it just so happens that standard deviation, which is also the square root of the variance, is given the little term there of sigma. That looks like a delta. We'll try that one again. It should be a little circle with a hat. All right, so one more time, little circle with a hat. That's sigma, and it stands for the standard deviation. How do we work all this stuff out? I'm just about to show you with a wonderful example from Cambridge. Really long video, I'm sorry about this, but it's actually important. So, the following example is taken from Cambridge. The number of chocolate bars X sold by a manufacturer in any month has the following distribution. What is the probability that X takes a value in the interval of mu minus 2 sigma to mu plus 2 sigma? So trying to find probabilities, which is this value here. So the question firstly has mu and sigma. So the hint here is that I actually need to find the value of mu and I need to find the value of sigma. So the value of mu, if you remember, is this times this times this times this times this times blah, 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 blah. Right? So I'm going to work that out and then hopefully fast forward this video so that you don't actually have to watch me work this out. So my calculator is telling me that the value of mu in that situation is 225. That's my long-term value. Now we're going to go and work out sigma. How do we work out sigma? Well, first thing we need to do is we need to find the variance, because we know that sigma is the root of the variance. And we know that the variance is given by e of x squared minus the e of x all squared. Well, we've already got the e of x all squared now, because that's what this value is here, e of x, so we can square that in a moment, but we need to find this e of x squared. So I'm now going to do my variance. How do I do that? Well, the good news is I've already scaffolded my calculator to actually have that information for me. So I'm going to now copy all of this, because my CAS allows me to copy all of this down, just so I don't lose my original value. I'm going to go back to the front, and I'm going to say 100 squared, 150 squared, 200 squared, 250 squared, 300 squared, and 400 squared. Yep, I think that's all my values, times 0.05, press enter, gives me my variance of, sorry, doesn't it? It gives me my e of x squared as 55000. So, using that variance formula there, e of x squared we know is 55000 minus 225 all squared, which gives me a fabulous value of minus 225 squared, 4,375. Now that's my variance. If you remember, I need to find my standard deviation, which is the square root of my variance, which is the square root of 4375, which gives me, what do we do? We go keyboard, and we go square root of my answer, please. Gives me 66.14378 ... Now I'm going to leave all those dots in for this moment in time, because I'm not going to round my calculator until later on. So I now need to find my probabilities of mu minus 2 sigma. So mu minus 2 sigma to mu plus 2 sigma. And how do we do that? Well, we literally just do mu minus 2 sigma. So what is my value of mu? We said my value of mu was 225 minus 2 times, and I'm going to copy that previous value in and leave all those decimal points in. So 92, can't read, 92.712 x, and now going back to my calculator, I'm just going to change that to a plus, and I get 357.287. 357.287. Now, do we have a value in my table of 92.712 and 357.287? Well, you're going to say, well, where am I looking? Well, these values here are saying we're trying to find the values, the probabilities, or sum the probabilities between an x of 92 and an x of 357. Well, I can't see those values, so I have to choose values inside of each of those points. Inside of 92.712, well, actually, that's 100 is my start value, but less than 357, which gives me 300. So we are going to try and find or add all of those probabilities between 92 and 357. So just making that more sensible, we have 100 and 300, which is what we can do. And so I'm going to add together 0.05, 0.15, 0.35, 0.25, and 0.15. Or, easy, do 1 minus 0.05. And what do we notice? We notice that the probability works out to be roughly 95%. Oh, 95. Get that right. 0.95, which just so happens to be 95%. Hold on. Didn't we meet that earlier? Didn't we say that between two standard deviations of the mean was roughly 95%? It was. Wow, this math stuff is freaking awesome. Ladies and gentlemen, I know that was a long question. I know that was long, but hopefully worthwhile. Using all of this information is going to make life absolutely zing for you for the rest of this chapter. Now, I'm on Patreon. If you can, do me a favor, click on the link shown below here and in the comments or in the description to go over to Patreon, and if you can, give me a hand in helping me create these videos. If not, and you're watching on YouTube, here we go. Click that button there. It says subscribe. I'm so excited. Otherwise, there's a video coming up. I won't hold it against you if you don't subscribe. No, please subscribe. It's been good seeing you. Thanks very much for your time. I look forward to seeing you next time.